You know from years in math classrooms that there is a clear expectation of reporting solutions in what we call simplified form. Why? Because there are frequently infinitely many variations on a particular answer, and we'd like to reach a common, recognizable version of that answer. Here's 4 examples to jog your memory. Let's start with the most basic, and that is that fractions must always be reduced or simplified, except in extenuating circumstances. But by and large, if you meet a fraction, use a fraction, you have to simplify it. So a common example would be I'm working on a problem and I end up with the answer 75 hundredths. That's a legitimate answer, but because there are infinitely many variations of it, let's say that I take it down to the form 15 twentieths. That is not entirely simplified at this point. I have divided both top and bottom by 5, but 15 and 20 continue to contain common factors. So it's not until I get to the version 3 over 4 that this is considered to be totally and utterly reduced or simplified. All of these are equivalent to one another, but the version that is universally accepted is 3/4. So I'd say the vast majority of time in your mathematical work, when you encounter a fraction, you should be sure to simplify or reduce it fully. Moving on, the next example is that powers of I, that imaginary unit that you've just met and started to work with, must be simplified. So as kind of a reference point, we have discovered that I works in what's called a modular arithmetic system, which is just a fancy way of saying that it really exists as one of 4 answers. I itself is defined as the square root of -1. I squared is defined as -1. I to the third is defined as -I, and I to the fourth is the same as -1. So after this point, if we go to the I to the fifth, we just end up with I again, and I to the sixth is equal to -1. So this is cyclical. You're just kind of repeating this cycle of 4 values over and over again. What that means is that if I am confronted with some version of I to some other power, let's say I'm confronted with I to the 19th, then I cannot leave that in its present form. It's not wrong, but it's not simplified and therefore unacceptable. So, I've created other videos addressing this point, but let's say one way that I want to simplify this is to recognize that I to the 4th to another 4th power is I to the 16th. And then if I were to multiply by I to the 3rd, I'd get all the way to I to the 19th. Now, why this particular arrangement? Because I to the 4th is just -1. So, and actually, this is not a -1, excuse me, this is a +1. That's a misstep on my part. I to the 4th is actually a +1. So I to the 4th is 1, and 1 raised to the 4th power is 1, times I to the 3rd. I to the 3rd is -I, so we're really just looking at an answer of -I. The bottom line here is that if you have I to any power, if it exceeds any of these, you've got to kind of simplify it so that one of these 4 answers shows up, either I, -1, -I, or +1. So that's the second example of how problems there's an expectation of simplification. Let's move to another example here. Expressions must be fully factored, not partially factored. So what do I mean by that? Well, we spent considerable time factoring quadratics for the purpose of solving them, but you can fully factor something or you can partially factor it. So, for instance, let's say we have 20x to the 3rd minus 16x squared. This is not quadratic, this is cubic. One person might recognize that the 20x to the 3rd and the 16x to the 2nd have a common factor of 2x, which is correct. That is a common factor. And so your factored form would be 10x squared minus 8x. However, this would not be considered the fully factored form because you have not successfully identified the GCF. So 2x was a factor, but it was not the greatest common factor. So just for emphasis, I'll switch colors, and the greatest common factor is actually 4x squared. And that would leave behind a binomial of 5x minus 4. So this would be considered the official fully factored version. And it falls nicely into this theme of what does it mean to do something fully or to completion. And so one final example, and this comes from our recent kind of explorations as well. And it is this idea that radicals cannot contain nth roots. And the radicals that we've been working with, and I'll stick to those in this video, have been square roots. But just in general, when I say nth roots, I mean that when you have a radical expression, this value here is known as the index, or we often in math use the letter n to say the nth root. Very commonly we use the second root, so the second root of 16 is 4, but it's so common that when we don't include that number, it's assumed to be 2. The index is assumed to be 2 if you don't write it in. So even when you see this notation, this is not a 0, it's a kind of a space, a placeholder, this is 4. You can have other n values. You could have the cube root of 8, for instance, which would be the number 2, meaning that 2 to the third is 8. So radicals cannot contain nth roots. Here's an example of that. Let's say I'm being asked for the third root of 32, and I'm looking for factors that are cubed numbers, not squared numbers, but cubed numbers, and I come up with 4 and 8. And upon further breaking this into pieces, recognize that the cube root of 8 is really just the number 2, and there is no cube root of 4. And so my final answer here would be 2 times the cube root of 4. What I have done is ensure that the radical, this value here, under the radical sign, is known as the radicand. But radical values or radical expressions cannot contain nth roots. There's no more perfect cube roots inside of 4 for me to exploit. And so, I hope I've made the point that I wanted to make, which is you've been simplifying expressions for the duration of your math career. That takes us to the present challenge right here. Our present situation is that denominators of fractions must be what we call rationalized. Just the other day I showed you the number systems again, and you recognize that some numbers are rational. They can be written as a ratio or comparison of one number to another. A very basic example would be 2/3 is a rational number. The number 7 can be written as 7/1. Anything that can be expressed as a ratio is a rational number, whereas again, values like pi or the square root of 2 cannot be written as ratios. Therefore, they are known as irrational numbers. And mathematicians will not allow irrational values to exist in a denominator as part of a final answer. So let's have a look at a real basic example. Let's say you are doing a math problem and end up with an answer 8/√2. This is viewed as unacceptable because the square root of 2 falls into the family of irrational values. So what we're trying to do here is come up with a way to change the way that this expression looks, but not what this expression means. And the way to do that is to multiply by the number 1, but disguised as something else. So anything divided by itself is 1. This is really just a glorified way of saying the number 1. Now, why did I choose this version? Because in the denominator, if you take a radical, a square root that is, and multiply it by itself, look what you've got. You've now got the square root of 4, and up top you've got 8√2. It actually looks pretty messy, but in actuality, you end up with 8√2 over simply the number 2, and 2 now has gone from being root 2, which was irrational, to being 2, which is totally and completely rational. You should also recognize from our earlier lessons that there's an opportunity to simplify here. You have 8√2s, but you're being divided by 2, so you end up with 4√2. This would be considered the final answer here. We have successfully rationalized the denominator, took it from what was irrational to something that is rational. The denominator is now just the number 1. These problems can become slightly more interesting and sophisticated. Here's another example, where now instead of just having one value in the denominator, I have a binomial. So let's do 7/4 plus √3. Here, if you try to multiply by a clever name for 1, let's say you multiply by √3, I'll let you do that on your own. You'll find that it does not rationalize the denominator. Doing this worked here when it was just one radical value, but as soon as you combine a radical value with some real number like this, 4, and you have this binomial, this method no longer works, so you have to tailor the method a little bit. And so the version of 1 that we want here is actually a beautiful version of it, known as the conjugate. And it looks like this. It's 4 minus the root of 3. 4 minus the root of 3. So let's do some multiplication here. Up top, we're going to get 7 times 4 is 28. 7 times this is negative 7 root 3. And here's where the magic happens down below. We're multiplying this binomial times this one. 4 and 4 give us 16. On the outside, we get positive root 3 times negative root 3 is negative root 9. In the middle, we get positive 4 root 3. And on the outside, we get negative 4 root 3. You might be looking at this and saying, there's no way this is going to end up rationalized and clean and neat. But it is. In the denominator, we've got 28 minus 7 root 3. Check out what happens here. 4 root 3 minus 4 root 3, they cancel out. And then this 9, the square root of 9 is just 3. 16 minus 3 is 13. And lo and behold, the question is not, is this pretty to look at? The question is, we started with an irrational denominator, and we ended up with a totally rational denominator. So the process is successful. I'll end the video with one final example, this time involving imaginary numbers, because I want to kind of bring that into the fold as well. So here's our last example in this video. You've got 2 minus I over 5 plus 2I. And this is not considered to be simplified because, again, what can we not have in the denominator? We can't have irrational values. And the square root, or the value I is defined as the square root of negative 1. And this value is deemed unacceptable. You can't have i's in the denominator. You can only have real values in the denominator. So not just rational, but also real. But what's familiar is we're going to be able to make use of, again, what's called the conjugate. And I'll say a little bit more about what I mean by conjugate. Conjugate in mathematics means that I've taken whatever binomial already exists, and I've used that binomial with the opposite sign in the middle. So 5 plus 2i is the conjugate of 5 minus 2i, and it's spelled this way, so that if you want to look it up and Google it, you can. These are known as conjugates. So let's do one final multiplication and see, will we end up with a denominator that is not only rational but also real. Let's do this carefully. 2 and 5, we're going to get 10. In the middle, we're going to get negative 5i. On the outside, we'll get negative 4i. And at the very end, plus 2i squared. Down below, we're looking at the product of these two. 25. Now, you should already know the middle and outer terms will cancel each other out, leaving me just with minus 4i squared. Time to play cleanup. 10, these two are like terms, minus 9i. Remember that I squared is defined as negative 1, so this is really just a negative 2. All over 25 minus 4 times negative 1. And when all is said and done, 10 minus 2 is 8, minus 9i. All over 25 plus 4, which is 29, totally rational, real denominator. The final piece of this puzzle is that when it comes to complex answers like this, and by complex, remember I introduced to you the complex number system, I mean that it's made up of both a real and an imaginary part. The convention for writing these is that we split them up. So what's being divided by 29? This entire numerator. So it's 8 divided by 29 minus 9i being divided by 29. And what we like about this answer is it falls into that a plus bi format, where this is the real part of the answer and this is the so-called imaginary part of the answer, and it's now in complex form. So that's it from beginning to end. Lot to follow, lot to digest, but it all boils down to this idea that answers must be fully simplified and that we have these conventions or agreements on what it means to be simplified.